Okay, so I had to leave class early today, so I'm doing the lecture on video. Um, what do you think of that? Video? Are you okay with the video lecture? Well, I'm sorry to disappoint you. I know you prefer I'm live there, but you know, I've got to go to this meeting, so you're going to have to deal with it today. All right, so today we're talking about equilibrium of a rigid body in 3 dimensions. Last time we were doing 2 dimensions, this time 3 dimensions. So it's just a little more complicated. You got to be a little more careful with your cross products and so on. So let's get started and go to the board here. Okay, the general conditions for equilibrium are that, remember what we've got. We've got the sum of all the forces is equal to the mass times the acceleration. And we're talking about equilibrium, nothing's moving. So we have that the sum of all the forces is equal to 0. And the corresponding equations is that the sum of all the moments is also equal to 0. And remember, these moments are given by the R cross F. So the moment is R cross F, so we take the sum for each force, R cross F, from any point, and that has to equal 0 also. So these 2 vector equations give 6 equations in 3 dimensions, and the 6 equations are just this. It's that the sum of all the x components of the forces have to be 0, the sum of all the y components of the forces have to be 0, and the sum of all the z components of the forces are also 0. That's 3, and then we have the other 3 being from the moments. So the x components of the moments has to be 0 when you take the sum. The sum of all the y components of the moments is equal to 0. And same thing with the z components. So there we go. We've got 6 equations, and they can be solved for, of course, up to 6 different unknowns. Now remember, I was telling you that the key to all these things are the connections. So the problems that we always deal with are, what are the reaction forces in statics? That's what we're looking at. And the reaction forces completely depend on how the connections are made between the rigid body you're talking about and other things. So here's some more. These are from the book. We've got the ball you can see here, or it's just kind of like what I was calling a chair leg on a frictionless surface. Now the only reaction force that it can occur is a single reaction force shown here that's going to be perpendicular to the surface. So one unknown. Over here we've got a cable. That can also have a single reaction force, and it's of course just along the line of the cable. So a single force along the line of the cable. Then below, what do we have here? We've got a roller on a rough surface, or a wheel on a rail. These have 2 force components here in 2 different dimensions, and you can see one is perpendicular to the surface. That's the one we're showing here, F sub y they call it, and the other one they've got is F sub z, and that is along this axis. So it can resist a force. It's on a rough surface, it's on a rail. It can resist a force that way. But if the force is along this line where the wheel is rolling, it'll just move along. So there's no F sub x force here. Here's some more connections. So what we've got here, they say this is, I would call like a chair leg on a rough surface, and or equivalently a ball and socket. This is kind of makes it more explicit. And then we've got 3 force components. There's of course the one, so F sub y, one component normal to the surface, perpendicular to the surface, and then since this one's the ball and socket, you know, it can provide resistance along this x-axis and along this y-axis, and similar over here with the rough surface. Okay, and then we get into some more complex ones here. You can see this universal joint, whatever this thing is, provides these 3 force components and a single couple. This one, the fixed support, this is what I was calling a fence post last time, and it just looks like a post sunk into the ground, and then that provides support on, you can see all 3 forces and all 3 couples. And I'm not going to get into them, but there's some more here. You can see hinge and bearing support, what this can do, pin and bracket. You can see. So there's all sorts of different things. You could use this, where is this? This is in the book, figure 410, as a reference when you run into one of these problems, which we'll see a lot of them this week. Okay, so I wanted to do this problem next. This sample problem. Here it is. Okay, we've got a 20-kilogram ladder used to reach high shelves in a storeroom, is supported by 2 flanged wheels A and B. So here's A, B. Those are the 2 flanged wheels mounted on a rail. That's a, you know, that tells us something right here. Mounted on a rail. Wheels on a rail. We just looked at those. So that's one of the connections. And by an unflanged wheel C, that's over here, the unflanged wheel, resting against a rail fixed to the wall. An 80-kilogram man stands on the ladder and leans to the right. The line of action of the combined weight W of the man and ladder intersects the floor at point D. Okay, so that's going to be the weight. We've got the weight is the 20 plus the 80 plus the 20. So the weight's 100 kilograms times G. And you can see where that point is. Here's our problem, determine the reactions at A, B, and C. Okay, simple enough problem, straightforward. Let's first look at a strategy. Let me write down a strategy here. Okay, so I don't have to draw it. Here's the picture of what we've got. Now, what I want to first do is establish a coordinate system. And what I'm going to do is pick my 0 point here, right at A. I'm going to have this be the x-axis, or I hat, you know, direction. The y will be going up. My y is going to go up this way. This is the X, Y, and then Z will be coming out. So I'm going to draw it this way. Okay, there we go. This is X, Y, Z, and there's my point of origin. Now what I need to do is draw the free body diagram. At A and B, we had flanged wheels. And what that meant was that it could support two forces in two different directions. One, it would be along the Z direction, and the second would be perpendicular to the surface, so that would be along the Y direction. Right here I've got two forces at B. One is heading up. I'll call that one B sub Y, and that's in the J hat direction. And then the second is acting in the Z direction. So that's going to be B sub Z in the K hat direction. And I've got the same thing at A. So I've got a force here and a force out this way. So I'm just going to write these down here. I've got A sub Z in the K hat direction and A sub Y in the J hat direction. So those are the reaction forces there. Up at C, I've got a single force that can just act perpendicular to that surface. So that's going to be like in this direction. We'll call that C sub K. And that acts in the going to call that C sub Z, and that acts in the K hat direction. Okay, so those are all the reaction forces, and then of course we've got this W force, and the W is, well, what did we say? It's 100 kilograms times G . 100 kilograms times G, and that acts in the we'll call it negative because it's going down. So it's a negative 100 kilograms times G in the Y direction. So J hat. That's that vector. Okay, so we've got the free body diagram here. And what I want to do, you can see all the dimensions are down here. One thing I wanted to do was do kind of a side view of this, just to look at the force due to this W. So if I look at a side view, I've got something like, okay, so this is the point C. So let's see, so this is kind of a side view looking at this angle, this point C, and then points A and B would be right here on top of one another, and this is the Z-axis, this is the Y-axis, and this side view, the X-axis, would be kind of coming out of the paper. So then I've got this ladder that looks something like this. Okay, something like that. And the weight is acting right here, and it goes of course, straight down. Okay, so if I look at this way, so I'm looking at this side view. You can see I can put some numbers in here. This is 3 meters from the origin up to C. And then this is the side view, so it's kind of going along here. And this should be 0.6 meters and 0.6 meters. So 0.6 meters from the origin here to where W comes down, and then another 0.6 meters from where W comes down to the places where A and B are. Where those wheels are. Okay, so that's the side view. We've got the force diagram here. And next, we just need to start writing down equations. So let's do that. I think the first thing we want to do is write that the sum of all the forces is equal to 0. So I'm going to write down all the forces. We had A sub y in the j hat direction plus A sub z in the k hat direction plus B sub y in the j hat direction plus B sub z in the k hat direction. Minus, that's the weight. I'm just going to put a W so I don't have to carry my numbers around. Minus the weight in the j hat direction. Plus, I had C sub z in the k hat direction. Now, okay, so that's the sum of all my forces. Here's the force on A, force on B, the weight, and the force on C. That's the sum of all my forces, and that equals 0. Now, what do we do here? Now we just collect the things. So we need all the j hats have to equal 0, and all the k hats have to equal 0. You can see there's no I hat forces. So what do we have? We have I'm just going to do the j hats first. A sub y j hat plus B sub y j hat minus W j hat equals 0. These are the j hats. And then I'll do the k hats also. So I've got A sub z k hat plus B sub z k hat plus C sub z k hat equals 0. So that's the k hats. So I did my sum of the forces equals 0. Next, I'm going to do the sum of the moments is equal to 0. So let's write that down. Sum of all the moments equals 0. Remember, the moments are R cross F for each force equals 0. Now, let me go back up a second. Okay, so I need to do it for each force, and I remember we had to pick a point. I picked this as my origin. We're going to compute the moments about point A. So the R to all these forces at A are 0. Those are 0. Then I just have to do R cross F for the forces at B, R cross F for the forces at W, and R cross F for the forces at C. Okay, the R vector from here, from our origin where I'm going to compute my moments, to B is, if we look at this, it's 0.9 plus another 0.3, so it's 1.2 meters along the x-axis there. So, well, let me write this down. So I'm doing these now. I've got 1.2 meters along the I hat direction. That's the R. Now you have to cross it with the force at B. And that has, the force at B is B sub Y in the J hat direction plus B sub Z in the K hat direction. Okay, now next I'm going to do R cross F for the force at the weight. Okay, so here I am. There's the weight. You could see, this is kind of a shortcut, but you could see that the weight acts in the same direction as the Y direction. Because of that, in the cross product, there's not going to be any, we don't need to know the R in the Y direction. So I'm going to write down the R vector just to this point D. And use that. So if you, let's see, you could put in some number if this is what you want to try, and you'll see this if you do the cross product. But say this is, it's not given here, but just say it's at like 2.7 meters. So you could use 2.7 meters in the J hat. And you'll see that if you do the cross product, it won't matter what the height, exact height is. So here's, I'm going to write the R vector from the origin to that point D. And this R vector is 0.9 in the I hat direction, and then minus 0.6 in the K hat direction. So again, that's the R from the origin to point D. And what I'm telling you is that if you put in, well, let me do the other part here first. We're going to cross that with the weight. And I'm just going to call it minus weight in the J hat direction. Okay. So again, this is, we've got R cross F for these are the forces acting at B. The R cross F for forces acting at A were all 0 because the R vector is 0. R cross F for forces acting at B. R right here. This is the R cross F for the weight. And now I just need to do the final one, which is the R cross F at the at point C. Here, so I'm going to write it down. It is, here's the R vector. It's 0.6 in the I hat direction. plus 3 in the j hat direction minus 1.2 in the k hat direction. So that's the r vector to this point C, crossed with c sub z in the k hat direction. Now this is the sum of the moments equals 0. Here's all the moments. That whole thing equals 0. Now when you go through and compute, so these are cross product, vector cross products, you'll need to get the signs right. You don't just go this times this. It depends on the order, I, J, K, whatever. But when you go and do these cross products, this is what you'll get. I'm going to write them down here. 1.2 b sub y in the k hat direction minus 1.2 b sub z in the j hat direction. So look, you could see this one 1.2 I hat crossed with this vector. We get this I, J, K with a plus sign. We do this one 1.2 times BZ, but I hat crossed with K hat is negative J hat. So on. So you have to get those signs right. So let me see, they put in the W. I'm going to put this in now. W equals, what was it? It was 100 kilograms times 9.8 meters per second squared. So if you put those numbers in and then multiply this out, you get this. We've got a minus, I'm just going to round up, 883 K hat minus 589 I hat minus, now I'm down on this one, 0.6 c sub z in the j hat direction plus 3 c sub z in the I hat direction. So that all thing equals 0. Let me show you something here. You can see when we did this was the R here from the origin to C vector crossed with this C sub Z, this one, K hat vector. What you could see, let's see, we've got the 0.6 CZ, I hat, K hat, so that's negative J hat direction. 3 CZ, it's a J hat crossed with a K hat, so it's positive. And then we had this one, negative 1.2 K hat crossed with the CZ K hat. Doesn't matter, it's 0. Because a K hat cross K hat is 0. And we're going to do something similar down here and try and get a... We'll do this for each of the 3 vector directions. So let me do the I hats. So let's see, I've got this, and this is in the I hat direction. So I have 3CZ minus 589. These are the I hats. equals 0. That's from the I hats. The j hats, I'm going to go down here, it's minus 1.2 bz. So this j hat one. Then what do I have? This one. Minus 0.6 cz equals 0. That's again from the j hats. And then I can do the k hats. We've got this one, k hat. There's two of them here. And I have 1.2 b sub y. And I have minus 883 equals 0. This is the k hats. Okay, so we've done all that. You can see you can start solving now. This is a simple one. We can get just use our algebra and get from here c sub z has to be equal to 196, and we're dealing with newtons. That's rounding things. Then once I've got that, I can plug it in here, and I can get b sub z right here, and that's a negative 98. Again, I'm rounding things here. And we can solve for b sub y right here. That's 736 newtons. Okay, we've got these three. So we've got c sub z, b sub y, b sub z. We have to go back up here with these two equations, and let's see, we've got, you can see we've got b sub y, we know the weight, b sub z, c sub z, so then we can just solve for a sub y and a sub z using these equations up here. And I'm just going to write them down. It ends up being a sub y equals 245 newtons, and a sub z equals negative 98 newtons. Again, I'm rounding off here. And let's see, so I can just get to the final answer here, which was what were the reactions at the 3 points. So we need vectors. So there's 3 vectors. The reaction at A, you know, and it would look like this. It's 245 newtons in the j hat direction, minus 98 newtons in the k hat direction. So that would be the reaction force at A. The reaction force at B, we've got right up here. It also is just in the j hat and k hat direction, so it's 736 newtons in the j hat direction, minus 98, same as A, 98 newtons in the k hat direction. And then the reaction force at C just had one component, and it was 196 newtons in the k hat direction. Okay, so these are the reaction forces, and that finishes today's lecture.